Hi and welcome to the DE Physical Education Flip Learning videos. The energy continuum of physical activity. Key terms you should know before starting this section. Energy continuum is a term which describes the type of respiration used for physical activity. Whether it is aerobic or anaerobic respiration depends on the intensity and the duration of the exercise. Energy transfer in the body. When we start to exercise, the demand for energy will rise rapidly. The energy continuum is a term used to describe which energy system is used for the different types of physical activity. It refers to the contribution that the different energy systems make to the production of energy depending on the intensity and duration of the activity. The three energy systems do not work independently of one another. Therefore, the ATP-PC system can't work on its own and neither can the other two. They all have to work simultaneously to different extents. They all contribute during all types of activity, but one of them will predominantly be the energy provider. The intensity and the duration of the activity are the factors that decide which is the main energy system in use. For some activities, which take an elite performer approximately 10 seconds to complete, the ATP-PC system will be the predominant energy system. In contrast, a marathon is a long duration, lower intensity activity, so the aerobic system will be the predominant energy system. As we look here on the scale of 100% aerobic activity or 100% anaerobic activity, and here are four athletics events. If we're looking at a 100-meter race, it's going to be towards the anaerobic activity. 400 meters would sort of be towards the 100% end. Our 1500 meters, again, towards the aerobic activity. And our marathon runner will be predominantly towards the aerobic activity. For the four examples previously, they're almost like in their purest form. Like a 100-meter runner is running as quick as they can, therefore it would be ATP-PC. However, what happens in an invasion game where you're stopping, you're starting, you're sprinting, you're chasing a ball, all those different things? The intensity level is constantly changing. Therefore, there'll be a mix of all three energy systems as the main energy provider. The energy continuum is often explained in terms of threshold. The ATP-PC and anaerobic glycolic threshold is the point at which the ATP-PC energy system is exhausted and the anaerobic glycolic system takes over. Hopefully you can see in the diagram below. As the ATP-PC runs out, this is the threshold as the two take over. So the anaerobic glycolic system would take over, and again the threshold between the anaerobic glycolic system and the aerobic system is where one runs out and the other one begins. The ATP threshold will end at around 10 seconds. The lactic acid will be about 3 minutes, and the aerobic system will continue going depending on the fitness of the athlete. Differences in the ATP generation between fast and slow twitch muscle fibers. Slow twitch muscle fibers are used for low to medium intensity activity, therefore use aerobic respiration as their main method of receiving fuel. Fast twitch muscle fibers are used for high intensity activities such as sprinting and use the anaerobic respiration as their main method of receiving fuel. Anaerobic respiration is much quicker than aerobic respiration but is less efficient process, producing only 2 ATP per glucose molecule. The muscle also fatigues much quicker due to the buildup of lactic acid. If we summarize the two, the slow twitch muscle fibers, their main pathway for ATP production is the aerobic system. It produces the maximum amount of ATP available from each glucose molecule, around 36 ATP, and the production is slow. They are more endurance based and are less likely to fatigue. If we're looking at fast twitch muscle fibers, the main pathway is the ATP production is via the lactate anaerobic energy system during glycolysis. The ATP production is an absence of oxygen and therefore not efficient. Only 2 ATP are produced per glucose molecule. Production of ATP this way is fast but cannot last for long periods of time, as these fibers have least resistance to muscle fatigue. Here's a sporting example of the predominant energy system that would be used. If the duration of the performance lasts less than 10 seconds, it would be the ATP-PC, for example 100 meters or long jump where it's an explosive performance. If it's around 8 to 90 seconds, it will be a combination going through that threshold of the ATP-PC and the anaerobic glycolic system, for example 200 meters, 400 meters, gymnastics. For 90 seconds to 3 minutes, it will be the anaerobic glycolic system, and towards the very end of it, it will be going into that threshold where the anaerobic system takes over, for example 1500 meter or a round of boxing. Anything that is longer than 3 minutes will be the aerobic system as its main energy provider. Key terms you should know. Oxygen consumption. This is the amount of oxygen we use to produce ATP. VO2 max, the maximum volume of oxygen that can be taken up by the muscles per minute, and submaximal oxygen deficit, when there is not enough oxygen available at the start of the exercise to provide all the energy aerobically. Energy transfer during long duration, lower intensity activity. Exercising for long periods of time at low intensity uses the aerobic system as its preferred method of producing energy. This is because at low intensity exercise, the demand for oxygen can be easily met and glucose can be broken down more efficiently when oxygen is present. Fats are used for energy at low intensity, but as the intensity increases, their usage becomes limited because they require more oxygen than the glucose to break them down. As soon as oxygen supply becomes limited, the percentage of fat that is used for energy drops. Oxygen consumption during exercise, maximum and submaximum oxygen deficit. When we exercise, the body uses oxygen to produce energy, to resynthesize the ATP. Oxygen consumption is the amount of oxygen we produce ATP and is usually referred to as VO2. At rest, we consume a rate of approximately 0.3 to 0.4 litres per minute. At the start of exercise, we use more oxygen to provide more ATP, so that oxygen consumption increases. As the intensity of the exercise increases, so does the amount of oxygen consumed, until the performance reaches maximum oxygen consumption, which is around 3 to 6 litres per minute, depending on the fitness of the athlete. This is called our VO2 max. When we start to exercise, insufficient oxygen is distributed to the tissues for all the energy to be provided aerobically. This is because it takes time for the circulatory system to respond to the increase in the demand for oxygen. Additionally, it also takes time for the mitochondria to adjust to the rate of aerobic respiration needed. As a result, energy is provided anaerobically to satisfy the increase in the demand for energy until the circulatory system and mitochondria can cope with the demand. This is referred to as submaximum oxygen debt. Maximum oxygen deficit is usually referred to as a maximum accumulated oxygen deficit, or MAOD. MAOD gives an indication for an anaerobic capacity. As you can see below, the oxygen deficit is bigger during maximum exercise as the performer is short of more oxygen. At the start they have to work anaerobically, hence the idea of maximum accumulated oxygen deficit. If you think about Usain Bolt when he sprints, for the first 8 seconds he is not using oxygen to provide energy, so his respiratory system would be anaerobic, as you can see on the right here. When we're using light exercise, for example if you were just sprinting for a ball that maybe took 1 or 2 seconds, the oxygen deficit will be smaller because you are not working anaerobically for as long a time as Usain Bolt when he's sprinting. Key terms you should know. EPOC, the amount of oxygen consumed during recovery above that which would be have consumed at the rest during the same time. Oxygen consumption during recovery. Recovery involves returning the body to its pre-exercise state. When a performer finishes exercise, oxygen consumption still remains quite high in comparison with oxygen consumption at rest. This is because extra oxygen is needed to be taken in and used to try and help the performer recover. This is often why you pant after you've finished exercise or you breathe deeply. The breathlessness after exercise is often referred to as an excess post-exercise oxygen consumption, or EPOC. Excess post-exercise oxygen consumption. There are 2 main components to the EPOC, the fast component and the slow component. The fast component. The fast replenishment stage uses the extra oxygen that is taken in during recovery to restore ATP and phosphocreatine and to resaturate the myoglobin with oxygen. For complete restoration of phosphocreatine, it takes around 3 minutes. However, 50% of the stores can be replenished after around 30 seconds, during which time approximately 3 litres of oxygen are consumed. Myoglobin has a high affinity for oxygen. It stores oxygen in the sarcoplasm that is diffused from the hemoglobin in the blood. After exercise, oxygen stores in the myoglobin are limited. The surplus oxygen supplied through EPOC helps replenish these stores, taking up to 2 minutes and using approximately 0.5 litres of oxygen. The slow component. The oxygen consumed during the slow replenishment stage has several functions: the removal of lactic acid, the maintenance of breathing and heart rates, the the glycogen replenishment, and the increase in body temperature. The slow component, removal of lactic acid. Lactic acid accumulates during exercise, and during recovery it needs to be removed. Full recovery may take up to an hour or longer, depending on the intensity and duration of the exercise. Lactic acid can be removed in the following ways. When oxygen is present, lactic acid can be converted back into pyruvate and oxidized into carbon dioxide and water in inactive muscles and organs. This can then be used by the muscles as an energy source. Transported in the blood to the liver, where it is converted into blood glucose and glycogen. This is known as the Cori cycle. It can also be converted into protein, and it can be removed during sweat and urine. The majority of lactic acid can be oxidized in the mitochondria, so performing a cool down can accelerate its removal. This is because exercise keeps the metabolic rate of the muscles high and keeps capillaries dilating. This is where oxygen is flushed through, removing accumulated lactic acid. The slow replacement stage of the recovery begins as soon as the lactic acid appears in the muscle cells and will continue using breathed oxygen until recovery is complete. This can take up to 5 to 6 litres of oxygen in the first half an hour of recovery, removing around 50% of the lactic acid. Key terms you should know: the Cori cycle. This process is where the lactic acid is transported in the blood to the liver, where it is converted to blood glucose and glycogen. The slow component, maintenance of breathing and heart rates. Maintaining breathing and heart rate requires extra oxygen to provide the energy needed for respiratory and heart muscles. This assists recovery as the extra oxygen is used to replenish ATP and the phosphocreatine stores. It resaturates the myoglobin and removes lactic acid, therefore returning the body back to its pre-exercise state. The slow component, glycogen replenishment. Glycogen is the main energy provider, and it is both a fuel for aerobic and anaerobic glycolic system. It will be depleted during exercise. The replacement of glycogen stores depends on the type of exercise undertaken and when and how much carbohydrate is consumed following exercise. It may take several days to complete the restoration of glycogen after a marathon, but it is less than an hour after high duration, short intensity exercise. A significant amount of glycogen can be restored as lactic acid and is converted back to blood glucose and glycogen in the liver via the Cori cycle. Glycogen replenishment, nutritional windows for optimal recovery. Eating a high carbohydrate meal will accelerate glycogen restoration, as will eating within 1 hour following exercise. There are 2 nutritional windows for optimal recovery after exercise. The first window is around 30 minutes after exercise, where both carbohydrates and proteins can be consumed in a 3:1 or 4:1 ratio. The combination of carbohydrates and proteins helps the body resynthesize muscle glycogen much more efficiently than consuming carbohydrates on its own. The second nutritional window is around 1 to 3 hours after the exercise and should be a meal high in protein, carbohydrates, and healthy fats. The slow component, increasing in the body temperature. When temperature remains high, respiratory rates will also remain high, as this will help the performer take in more oxygen during recovery. However, extra oxygen is needed to fuel the increase in temperature until the body returns to normal. Energy transfer during short duration, high intensity exercise. During short duration, high intensity exercise, energy has to be produced rapidly. The aerobic system is too complicated to produce energy rapidly, so the body needs to rely on the anaerobic respiration using ATP-PC and the anaerobic glycolic system. However, these systems cannot produce energy for long periods of time. The ATP-PC system can only produce energy for high-intensity activities lasting 10 seconds. The anaerobic glycolic system can last for longer, but it depends on what intensity the performer is working at to how long it lasts. For example, if you think of a 400-meter runner, they're going to use the anaerobic glycolic system as their main system. However, they'll be exhausted around 45 to 50 seconds after running the event. They won't be able to run another 400 meters straight away. It will take them around 3 minutes to be able to build up the replenishments to be able to run again. However, if you think of an 800-meter runner, which is double the length of the 400-meter runner, it takes roughly 2 minutes. It will again use the anaerobic glycolic system. However, because the intensity is less, they will therefore be able to use the system for longer. Lactate accumulation. Lactate and lactic acid are not the same thing, but in terms are often used interchangeably. Using the anaerobic glycolysis system produces a byproduct called lactic acid as a result of glycolysis. The higher the intensity of the exercise, the more lactic acid is produced. The lactic acid breaks down, releasing hydrogen ions. The remaining compound combines with sodium ions or potassium ions to form salt lactate. Lactate accumulates in the muscles, more hydrogen ions are present, and it's actually the presence of hydrogen ions that increases the acidity in the blood. This slows down the enzyme activity, which affects the breakdown of glycogen, causing muscle fatigue. The lactate produced in the muscles diffuses into the blood, and the blood lactate can be measured. Key terms you should know before we start this section. Lactate threshold, the point during exercise at which lactic acid quickly accumulates in the blood. Onset blood lactate accumulation, the point when lactic levels go above 4 millimoles per litre. Millimole. A mole is an amount of substance that contains a large number of molecules or atoms. A millimole is 1,000th of a mole. As exercise intensity increases, the body moves from working aerobically to anaerobically. This crossing of the aerobic and anaerobic threshold is also known as the lactate threshold and is the point in which the lactic acid rapidly accumulates in the blood. We are constantly producing small amounts of lactate due to red blood cell activity when working at low intensity, but the levels are low and the body deals with these efficiently. However, as the intensity of the exercise increases, the body is unable to produce enough oxygen to break down the lactate. The levels of lactate build up and accumulate, and this is known as OBLA, onset of blood lactate accumulation. OBLA and lactate threshold are simply different ways of measuring the same thing. At rest, approximately 1 to 2 millimoles per litre of lactate can be found in the blood. However, during intense exercise, levels of lactate will rise dramatically. As it starts to accumulate, OBLA occurs. This is usually when the concentration of lactic is around 4 millimoles per litre. Measuring OBL gives an indication of endurance capacity. The lactate threshold and the onset of blood lactate accumulation. Lactate threshold is expressed as a percentage of VO2 max. As fitness increases, the lactate threshold becomes delayed. Average performers may have a lactate threshold that is around 50 to 60% of their VO2 max, whereas elite performers may have a lactate threshold around 70, 80 or even 90% of their VO2 max. Training has limited effect on VO2 max and is largely genetically determined. The big difference in performance comes from the delay of lactate threshold. When we exercise, we tend to work at or just below lactate threshold. In simple terms, as the level where we fatigue is not going to cause our performance to deteriorate. The fitter we are, the higher our lactate threshold as a percentage of our VO2 max, and hence the harder we can work. The multi-stage fitness test is a good practical example that illustrates OBLA. As the test becomes more and more demanding because of the reduced time to complete each shuttle, the performer eventually reaches a point where energy cannot be provided aerobically. This means the performer has to use the anaerobic system to resynthesize ATP. Levels of lactate produced in the muscles increase until eventually muscle fatigue occurs and the performer slows down or is no longer able to keep up with the beeps. Factors affecting the rate of lactate accumulation. There are 5 different factors that affect the rate of lactate accumulation: exercise intensity, muscle fiber type, rate of blood lactate removal, the respiratory exchange ratio, and the fitness of the performer. Factors affecting the rate of lactate: exercise intensity. The higher the exercise intensity, the greater the demand for energy, and the faster the OBLA occurs. Fast-twitch fibres are used for high-intensity exercise and can only maintain their workload with the use of glycogen as a fuel. When glycogen is broken down, the absence of oxygen in the pyruvic acid, lactic acid is formed. Factors affecting the rate of lactic accumulation: muscle fiber type. Slow-twitch muscle fiber types produce less lactate than fast-twitch muscle fibers. When slow-twitch fibers use glycogen as a fuel due to the presence of oxygen, the glycogen can be broken down more effectively and with little lactate production. Factors affecting the rate of lactate accumulation: rate of blood lactate removal. If the rate of lactate removal is equivalent to the rate to lactate production, then the concentration of blood lactate remains consistent. If lactate production increases, then lactate will start to accumulate in the blood until OBL is reached. Factors affecting the ratio of lactate accumulation: the respiratory exchange ratio. It is the ratio of carbon dioxide produced compared to the oxygen consumed. As the ratio has a value close to 1 to 0, glycogen becomes the preferred fuel and therefore is a greater chance of accumulation of lactate. Factors affecting the ratio of lactic accumulation: fitness of the performer. A person who trains regularly will be in a better position to delay OBL as adaptations occur to the trained muscles. increased number of mitochondria and myoglobin together with an increase in capillary density improve the capacity for aerobic respiration and therefore avoid the use of the lactic anaerobic system. Key terms you should know. Buffering. A process which aids the removal of lactate and removes the acidity levels in the blood and muscles. Lactate-producing capacity and sprint power performance. Elite sprinters and power athletes will have a much better anaerobic endurance than non-elite sprinters. This is because their body has adapted to cope with high levels of lactate. In addition, through a process called buffering, they are able to increase the rates of lactate removal and consequently have a lower lactate level. Buffering works like a sponge mopping up water, but instead it mops up lactate. This means that athletes will be able to work at high intensities for longer before fatigue sets in. As well as being able to tolerate high levels of lactate, the trained status of the working muscles would lead to an adaptive response. There will be a greater number and size of mitochondria, and the associated oxygenative enzymes increase the capillary density and more myoglobin.